Hello and welcome to my channel. Today I would like to talk about these great actuators. I receive a lot of comments and emails about how to use certain actuators. And quite often it's complicated to answer this question mainly because of the three main reasons. First of all, many companies they don't provide any manual or any example of the program how to control the actuators. And so like this you don't know the protocol and you just need to control it by magic or I don't know how. The second reason, some of the companies they change their protocol, and I saw this at least with the two really big actuator companies. They used one protocol for the CAN communication and after some time they decided to change this protocol out of no reason. You made your program for one protocol, now you need to change this protocol, and some of these companies they make this protocol even worse than it was before. This is not good. And the third reason is bad controller. It's the case when the actuator has either bad controller or either bad firmware on this controller, so that it's almost impossible to find the PID values with which this actuator works properly without any vibrations, without any jerky motion. And in order to address this issue, I have decided to develop my own actuators. Ta-da! It took me a couple of years to do this, but I think I use the advanced controllers, probably the best controllers. I use high quality motors and reliable reducers. So basically this I think the best actuators for not very high price. All these actuators they made out of metal, and I use the plastic only for the stand here and also for the cover. This is a cover which you need to take off when you use this actuator. So this is only protective cover in order to prevent the dust coming inside the reducer. The rest is aluminum and steel. Most of these actuators are harmonic drive based actuators, and some of them are quasi-direct drive actuators. Let's take a closer look. You can find the information about these actuators on my website, scientific.com. Let me show you. Look how beautiful is it. And there is some products over here. You can find them also over here. There is harmonic actuators, quasi-direct drive, only one actuator, yet 3D printed actuators, and consulting services. Let's look at the harmonic actuators. There are four different actuators, the less powerful one and more powerful one. H25, 48 Newton meters rated torque, H20, 32 Newton meters rated torque, H17, 19 Newton meters rated torque, and H14, 6.5 Newton meters rated torque. Let's look at the most powerful one. Over here you can see the 2D drawing of this actuator and the parameters, the main parameters. So it's controlled using CAN FD protocol, which is the fastest one. It uses a Motius driver. Maximum torque is 120 Newton meters, rated speed 24 RPM, rated torque 48 Newton meters, reduction ratio 50. The weight is a little bit more than 2 kilos, and the operating voltage is from 24 to 48 volts. And here's the size. Right now the lead time is between 2 to 6 weeks, but I'm working on making it shorter. Basically, in order to make it shorter, I need to have more orders. Let's look at another one. For example, this one. I think this one is quite interesting because it's not super expensive and at the same time it has quite good rated torque. It has a maximum torque 40 Newton meters, rated torque 19 Newton meters, and the weight a little bit less than 1 kilo. The same operating voltage as before, and here's the size. Also, let's look at the quasi-direct drive actuator. It's this one. It's based on the AK-109 from T-Motor company, or CubeMars. CubeMars is part of the T-Motor. And why I use AK-109? Because I think the hardware-wise it's really good actuators, but I don't really like the controller. And also I would like to have the multiple actuators with the same controllers. Like this you don't need to learn new protocol each time when you use the new actuator. So here's the parameters. The reduction ratio it's 9:1 because this is a quasi-direct drive. It's not very precise, it has a quite high backlash, but this is a normal for quasi-direct drive actuators. It's super fast, 130 RPM rated speed. It has a rated voltage again from 24 to 48 volts. Its weight a little bit less than 1 kilo. And the rated torque is a quite decent one. And on the home page you can see all of them together. This is a 3D printed one. And here some consulting services. Now let me show you how it's easy to use these actuators. In order to run such actuator, first of all, you would need to have actuator and power supply. I have here one example of the power supply. This is a 24 volts 5 amps with such connector at the end. Another very common power supply. This is a 48 volts 400 watts with the same type of the connector. If you want your PC or MacBook to communicate with this actuator, you can use either this kind of FD CAN USB adapter, or probably the better one would be to use this one, small one. It's quite cheap, and it's also from the MJ Bots company. It's called MJ CAN FD USB. With these two solutions, the easiest would be to use Python library. But also you can control these actuators using Arduino. This a board from Logan, you can buy it from the Seed Studio website. It's called CANbet FD. And this is basically an Arduino, so you can program it with Arduino IDE. And it has the CAN FD chip. The connection is super simple, it's shown over here. The black one is ground, the red one is CAN high, and the yellow one is CAN low, which goes to this connector just like this. Of course, you can use another Arduino board with appropriate CAN FD controller. This one is nice because it's quite cheap and it's quite small. If you are using the long cable for the data, for the CAN, this is not a long cable. I mean, when you're using the cable which is longer than 30 or 40 centimeters, or when you use multiple actuators connected together at the same CAN bus, you would need to put at the end of the CAN bus the termination resistor of 120 ohms, which you can also buy from the MJ Bots company, CAN Terminator. For the test, I have installed the actuators on the support, and I will also put this one on the output shaft like this. It's easier to see how it rotates. And for the harmonic actuator, I'm going to use the biggest one, 48 Newton meters rated torque. And for the computer, I'm going to use Jetson Orin Nano, because this is a great board, and at the same time it has an ARM processor, and it's a little bit trickier to install the software for the ARM processor for the Linux. So I'm going to show you kind of worst case scenario, so the most complicated installation. With the desktop PC, it's going to be even easier. Connection is straightforward. And the power. And this USB-C goes to the computer. Before showing you how to use the Python library, I would like to show you how to use tview program. With this program, you can easily check your actuator, and you can also change some parameters. So it's very useful, at least for the setup of your actuator. Most of the information about these controllers you can find on the GitHub page, MJ Bots modules. And specifically on the GitHub page modules doc getting started, you can find how to install the tview software, which is over here. Software. As I told you, it's easier to use the desktop PC. Like this, you need only to use pipe 3 install modules GUI. I'm going to use the Jetson, so it's more complicated case, and we should follow the instructions for the Raspberry Pi. So you can also use a Raspberry Pi. So first of all, I would need the pip command. So sudo apt install python 3 pip. Now let's copy these commands. So it didn't activate the environment, but this is not a problem. And let's copy these commands. So I'm just following the instruction. Nothing special here. Successfully installed. Perfect. Now let's go over here, and we need to do some special stuff because we're using the Linux. We're using the Linux, so we need to set up udev rules over here. This is easy, we just need to execute some commands. And we need this file, so let's get this file to the download folder. So we have this file in the download folder. This is perfect. Now let's go to the download folder, and we need to execute these commands. 1, 2, 3. Perfect. We don't need this anymore, except that we need to run the tview. And to run the tview, it's this command. Before we run this command, we need to switch on our actuator, so the put power to our actuator, and we need to connect the USB to our device. As you can see, there is some light. Ta-da! Now everything is connected, so we can run the tview. As you can see over here, it took some parameters from the actuator to show them. And now we can look at them. So let's go to the config and let's go to the ID. So the ID is 1. Here you can change the ID. And in order to save the new values, you can do the conf write. But we are not going to do this right now because I need to check the timeout. Default timeout is not a number. Perfect. This is what I wanted. This is a timeout. It defines how fast actuator should receive a command. And if the actuator does not receive the command in this specific time period, the actuator says that there is something wrong and it disables. For our test, we don't want this safety feature, so that's why I put the default timeout as not a number. To save the parameters is conf write. And also we can try to move our actuator. So let's go to the telemetry tab. In the telemetry tab, let's go to the servo stat. Here we can see the position and the torque. So let's plot the position on the left, on the right, okay, and the torque on the left. And by the way, here you can see the temperature of the controller board and the temperature of the motor. They are quite close, one to another. To run this actuator, we're going to use this command, and 1.0 means that the motor is going to turn one turn, and one turn of the motor is going to be 1/9 turn of the output rotor because of the reducer. We would like to use quite low torque, let's say 0.2 Newton meters, and we would like to run it slowly with the speed 2.0 and with acceleration 10.0. We can go to another position, for example, to the position 9 with the speed 20 and with acceleration 40. Let me show you how it rotates. Of course, you can adjust PID values. And in order to stop the motor is the command d-stop. So now the motor is enabled, so it holds its position. I cannot rotate it. But if we do the stop, it releases the output shaft, and so I can rotate it easily. But the position is still tracked, as you can see. Slow rotation. And faster rotation. Perfect. Now you know how to change the timeout, how to set the ID, and at the same way you can change the PID values and many other parameters. There are like tons of parameters. Next, let's look how to use libraries. I would like to show you how to use these actuators with the two libraries. Both of them the Python libraries. One of them is simple library, another one is more capable library. And I will start with more capable library. If you already installed the tview, you don't need to install anything special for these libraries. But if you have not, you need to install Python 3 serial. To do this, it's quite easy. What you need to do the sudo apt install Python 3 serial. Easy. And afterwards, you would need to also set up udev rules, which I already showed you how to do this. And when everything is done, you can copy the library somewhere. In my case, I put it in the documents over here, and I have two of them. Let's start with this one. Over here, there is 5 examples, which I think are quite interesting to look in order to understand how this library works. More information about these libraries you can find on the GitHub page of the Motius controller. But let's run one of these examples. For this, we need to switch on our actuator. The power to the actuator on, CAN to USB adapter connected to the Raspberry Pi. And now we can do the examples. The first example called simple.py. It shows some information from the actuator, like position, the mode, velocity, torque, voltage, temperature, And you can open this example in order to see how to do this. And after this example, the motor is enabled. And in order to disable it, we need to run the example number 2. Example number 3 prints the proportional term of the PID. And from this example, you can see how to change this term. Example number 4 is going to rotate our actuator in one direction, wait, and rotate it to another direction. And you can see some parameters. And the last example, it rotated our actuator in 2 directions, and afterwards it shows the position of the secondary encoder and the first encoder, and also the temperature of the motor over here, motor temperature. So there is a motor temperature, and just temperature is the temperature of the electronics, temperature of the driver. So this is the first library with the 5 examples, which I think should be enough for you in order to start. The second library only has 2 examples. It's an easier library, and it does not use the asynchronous module. So the first example shows some values like temperature and position. And the second example should move our motor. There's a delay between 2 motions. Yes. And again, it gives us some values of the position, velocity, torque, etc. And so this is examples of the 2 simple Python libraries which you don't really even need to install on your Jetson. It works just from the folder. I like when it's simple. And these examples should be enough in order to get started. Now let's look how to control this actuator using the Arduino. It's also easy. First of all, we need to install the modules library. It's already in the Arduino library manager. So all you need to do is go to the manager, type modules in the search, and you will find this library. When you install it, you will have several additional examples. They're over here. And one of these examples is wait complete, which is probably the most advanced example. And I use it over here. I modified it a little bit in order to make the motion a little bit wider to better see on the motor with the reducer. But I kept the speed quite low, the acceleration quite low, just to keep it simple. The code is already on the Arduino. What we need to do is just switch on this actuator and connect this Arduino board to the PC in order to have the power to the Arduino board, and also in order to read the values from this Arduino. And we see here the values, so which command was sent, the mode in which this actuator, 10 means that it's enabled, and the position, velocity, torque, and secondary encoder, which is not enabled, which is not connected here. And as you can see, it rotates in one direction and back. So this is example which is called wait complete. And over here it sends the command to the motor, and it waits until the command is until the motion is completed. So you put the position, you can put the torque, you can put other values, but here it's basically position. There is this value which you can find if you go to the GitHub of the modules. You can find this exact command set position wait complete, and you can find that this value is basically the period how often this function checks that the motion is completed. And it basically moves from the 0.1 position of the rotor to the 8.5. This is position in turns. Of course, there is no way to stop this by hand. I mean, not by normal hands. No way. It's so easy, so there is no much to explain here. Also from the MJBots company, you can buy these pieces. This is a termination resistor, 120 ohms. And this is the board which connects all these 3 connectors together. And with this you can build the robots without soldering the pieces. So here, for example, there is this USB to CAN adapter, which connects to the first board, to the first motor. Afterwards, the CAN bus goes to the second motor, and there is over here the CAN bus terminator. But you can connect as many actuators as you want. At least you can connect a lot of them together. Of course, I have not connected the power. This is just for the illustration. And of course, you would need to put different IDs for each actuator. You should not have two actuators with the same ID on the same CAN bus. But these are the small pieces which are quite useful. I have mounted the biggest actuator, harmonic one. Now it's holding position, and it's super rigid, like extremely rigid. So when I try to move it, it's actually a plastic base which moves. There is zero noticeable backlash. This is not yet maximum speed. This is going to be rated speed. I think it's quite fast. Let's put some weight. This is 4 kilo. It should not be a problem. It can be a problem for the plastic parts, but not for the actuator. Easy. But my table shakes. I can probably even increase the speed. I'm just afraid that the plastic parts are going to fail. At this point, it's 25 centimeters from the center. 10 kilos. But let's do it slowly. Easy. And now I installed the small actuator. This is H17. This is a slow speed. This is the fastest speed, not the maximum. And this is close to the rated speed. Again, it's super solid. The only flex is in the base. Four kilos. Easy. And I can also monitor the temperature like this. I know what happens with the motor. I know if it's too much of the load or not enough load. And the motor is still quite cold, 28.6. This should be close to the rated torque. So it's 8 kilos at 25 centimeters approximately. As you can see, it's quite easy to use these actuators. And I would like to remind you that the goal of these actuators was not to make the cheapest actuators. The goal was to make the best actuators for reasonable price. That's why it took me a lot of time to test these actuators and to select the best components for it. But I hope that you will find these actuators interesting and you will support me on this adventure. And thank you for watching this video till the end. Huge thank you to people who support me via Patreon and via YouTube channel membership. Here are their names. Thank you, you're the best. As usual, stay safe, good luck with your projects, and see you next time.